There's a gas sitting under your feet, right now, almost everywhere on Earth. And until very recently, almost nobody was looking for it. It's not oil, it's not natural gas, it's hydrogen, naturally occurring, geologically produced hydrogen. In this video, we're going to walk through what it is, how much of it might actually be down there, and why an idea that was dismissed for decades is suddenly one of the most talked about topics in energy geology. Let's get into it. First, let's set the stage with the hydrogen everyone already talks about, the industrial kind. Today, hydrogen is mostly used for petroleum refining, fertilizer, and petrochemicals. But look at where demand is headed. By 2050, we're projecting roughly 5 times today's demand, driven by sectors that are brutally hard to decarbonize: aviation, steel, heavy industry, mining. The problem is that almost all of the hydrogen we currently make, the blue and green kinds, is expensive and mineral-intensive to produce. Hydrogen, as most people think about it, isn't an energy source at all. It's a storage and transport medium, which raises the obvious question: what if we didn't have to manufacture it? What if nature was already making it for us? And it turns out, nature is. Natural hydrogen shows up almost everywhere we've thought to measure it. It's in the air at trace levels. The oceans are supersaturated with it. Soils show it at concentrations from 10 to over 1,000 parts per million. And in deep mines and boreholes, we've measured it at full percentage concentrations, orders of magnitude higher. This map shows surface observations of hydrogen seeps around the world. Notice the dense cluster over Eastern Europe and the former Soviet Union. That's not because hydrogen prefers that region geologically. It's because that's where people have actually been looking for decades. As one researcher put it, the more we look for hydrogen, the more we find it. So where does all this hydrogen actually come from? There are more than 30 known ways to make it geologically, but a few dominate. Serpentinization is the big one. Water reacting with ultra-basic, iron-rich rocks, splitting the water molecule and releasing hydrogen as a byproduct. Then there's radiolysis, radioactive decay in the crust literally splitting water apart. There's deep-sourced hydrogen, possibly primordial, or generated in the lower crust. And there are secondary pathways too: thermal breakdown of organic matter, even mechanical grinding of rock generating hydrogen through fresh mineral surfaces. Look at this chart. Serpentinite settings show by far the highest median concentrations. For a long time, the assumption in geology was that hydrogen is so small and so reactive that it simply couldn't accumulate. It would always leak away or react before it could pool. That assumption is now being seriously challenged. Here's the core insight that's driving this whole field right now. Petroleum geology spent a century mapping sedimentary basins because that's where oil and gas accumulate. But hydrogen generation is generally not happening in those same places. Petroleum exploration was never targeted at hydrogen. Mineral exploration typically doesn't even test for gas composition. And on top of that, hydrogen gets consumed by the very reactions that form hydrocarbons. Put simply, we haven't been looking for hydrogen in the right places with the right tools. And we have direct proof this works, because it already happened, almost by accident. In 1987, a water well drilling crew in Mali hit a gas pocket that exploded. Nobody knew what to do with it at the time, so the well was capped. In 2012, it was reopened and tested at over 97% pure hydrogen. Since then, exploration campaigns using seismic, gravity, and magnetic surveys plus coring have found multiple stacked reservoirs, sealed by dolerite rock. That original discovery well is still producing today, generating electricity for a nearby village. And here's the wild part: we still don't know exactly where the hydrogen is coming from. The estimated resource potential at this one field alone is around 630 billion cubic meters. So Mali proves it can happen. The bigger question is, how much natural hydrogen is there globally? Projected hydrogen demand by 2050 is around 430 million tons a year. Natural hydrogen generation in the subsurface is currently estimated at around 23 million tons a year. Do the math, and if we could somehow capture all of it, that's only about 5% of projected demand. But that comparison is actually the wrong way to think about it. Annual generation isn't the number that matters. What matters is how much has accumulated and been preserved underground over geologic time. That depends on trapping efficiency, residence time, how much gets consumed biotically or abiotically, and how good our exploration and production actually gets. To actually answer that accumulation question, researchers built a resource model, essentially a steady-state accounting system for hydrogen in the crust. Working from the bottom up, hydrogen is generated at depth, and that generation rate is estimated from direct observations. As it migrates upward, some is lost to biotic and abiotic consumption, and trapping efficiency for that step is borrowed from decades of petroleum system research. What survives gets trapped in reservoirs, where it can sit for a residence time estimated using helium and CO2 as analogs. And whatever escapes, trapping continues up to the surface as measurable flux. Today, the whole system is assumed to be at steady state. Under the hood, that model is a mass balance equation with time-dependent decay, essentially tracking how much hydrogen is trapped, generated, and lost over time, governed by a trapping efficiency term, a consumption fraction, and a split between shallow and deep loss pathways. Because so many of those inputs are uncertain, the researchers didn't run this once. They ran it as a Monte Carlo simulation, sampling generation rates, trapping efficiency, residence time, leakage, and consumption thousands of times to build a probability distribution rather than a single number. So what does that simulation actually produce? For hydrogen flux reaching the atmosphere, the most probable estimate, the P50, comes out around 20 million tons a year, though the full modeled range spans from under 1 to as much as 1,000 million tons. As a sanity check, an independent estimate of volcanic and hydrothermal flux alone comes in at about 9.5 million tons a year, in the same ballpark. Given just how many orders of magnitude these inputs and outputs can span, that level of agreement is actually pretty reassuring. Now for the number everyone actually wants. How much hydrogen might be sitting in the ground right now? The most probable estimate is around 5 million tons, but the full distribution spans from tens of thousands of tons to billions. Most of that is probably inaccessible, too deep, too far offshore, or in accumulations too small to matter. But here's the number that got everyone's attention. If we could recover just 2% of the low-end in-place estimate, 100,000 tons, that alone would supply all projected hydrogen demand for over 200 years. For scale, that's roughly comparable in energy content to the entire world's proven natural gas reserves. The real question isn't how much hydrogen exists, it's whether it's actually forming into accumulations we can find and produce. You'll see a lot of headlines calling natural hydrogen a renewable, limitless clean fuel. Let's pump the brakes on that. The most probable estimate for the renewable rate, meaning hydrogen actively regenerating fast enough to be continuously extracted, is only about 5 million tons a year globally, with just a 10% chance it exceeds 29. In other words, geologic accumulations of hydrogen are almost certainly not substantially renewable on human timescales. This is a resource you find and produce, more like a gas field, not a resource you can pump indefinitely like solar or wind. It's a useful counterweight to some of the more breathless, gold hydrogen coverage out there. To actually go find this stuff, geologists are borrowing a framework straight out of petroleum exploration, the petroleum system concept. For oil and gas to accumulate, you need a source, a migration pathway, a reservoir, a trap and seal, preservation over time, and the right timing between all of them. The hydrogen system needs exactly the same 6 ingredients. The names are identical. What's different is the geology underneath each one, which is what the rest of this video is going to dig into. There are actually 3 different conceptual ways to think about producing hydrogen. The first is natural accumulations, hydrogen that's already pooled up over geologic time, like Mali, where you need every single element of the system: source, migration, reservoir, trap, preservation, and timing. The second is natural generation, essentially intercepting hydrogen as it's actively being produced and migrating, without needing a trap at all. And the third is stimulated generation, actually engineering the reaction, for example, injecting water into iron-rich rock to trigger serpentinization on demand. Right now, the global resource models we just walked through only account for that first category, natural accumulations. Whether natural or stimulated generation can be made commercially viable is still an open question. Let's zoom into that first system component, source, a little more. Serpentinization, water reacting with ultramafic rock, remains the leading candidate. Radiolysis, the natural splitting of water by radioactive decay, is another. There's deep-sourced hydrogen, potentially primordial or generated in the lower crust. And there are secondary contributors, other redox reactions like the oxidation of iron in banded iron formations and organic maturation, where high-maturity organic matter breaks down and releases hydrogen as a byproduct. This chart shows measured generation rates across temperature, and you can see potential clustering in specific low and high temperature windows. But there are still real open questions here. What are the actual kinetics? What controls the rate? Are these reactions catalyzed by anything? And are there diagnostic geochemical fingerprints we could use to find them? Next, seals. This might be the single most critical and least understood piece of the whole hydrogen system. Hydrogen's kinetic diameter is smaller than methane's and close to helium's, which means it can slip through seals that would easily trap oil or gas. The good news: we know low permeability seals like evaporite minerals can hold on to helium for hundreds of millions of years, and the capillary entry pressure needed to push hydrogen through a seal turns out to be similar to CO2. In Mali, the accumulation is sealed by dolerite. But beyond that one case, we honestly don't understand seal capacity for hydrogen very well at all. How mineralogy, water content, and entry pressure interact is still an active research question. Even if hydrogen gets trapped, will it stay trapped? That comes down to migration and preservation, and temperature turns out to be the master control. Hydrogen, methane solubility varies by about 3 orders of magnitude with depth. At shallow, cooler settings, microbial consumption dominates. Bacteria happily eat hydrogen for energy. But go deeper and hotter, and biology shuts down, while abiotic reaction rates are still relatively low, which means deeper, hotter settings actually have a higher probability of preserving accumulations over geologic time. It's a bit counterintuitive. The cold, shallow zones you'd assume are safest are actually where microbes quietly destroy the resource. So that's the science of how natural hydrogen systems work. Now let's talk about actually finding it. A major prospectivity mapping effort set out to do 4 things. Produce a preliminary map of hydrogen prospectivity across the lower 48 United States, build a hydrogen system model purpose-built for that mapping, identify proxy datasets for each essential system component, and, critically, account for uncertainty in both the data and the model itself. That last point matters a lot, because as we've just seen, almost every piece of this system still carries real geological uncertainty. Here's how that mapping actually works under the hood. Raw, mappable datasets, things like magnetic anomalies, fault locations, rock type, get combined into interpreted maps for each system component. Source, migration, reservoir, seal. Those interpreted maps then combine into a single chance of sufficiency score. And the net result, layer by layer, is a local hydrogen prospectivity estimate for any given point on the map. This is the actual input table behind that model. 21 different data layers, each assigned a chance of sufficiency score from things like magnetic anomalies and failed rifts on the source side, to sedimentary versus non-sedimentary rock on the reservoir and seal side. I won't walk through every row, but the point is this. Every single layer in this table carries an explicit, quantified uncertainty. This isn't a black box map. It's a transparent, testable model. One important piece of this model is migration. How far hydrogen can travel laterally once it's generated. This first-generation model has real limitations worth being upfront about. It only considers lateral migration, not vertical. It's only modeled in sedimentary settings, and it uses a regional top basement surface to define flow lines and drainage areas, shown here across the central U.S. It's a first pass, not a finished picture. Zooming back out, here's what those component layers actually look like as maps. Source combines serpentinization, radiolysis, and cryptic deep source indicators. Reservoir maps sedimentary versus non-sedimentary rock. And seal and preservation is scored based on lithology-specific chance of sufficiency. Each of these is its own independent probability surface across the country, and they all get multiplied together in the next step. And here's the payoff. Source chance of sufficiency times reservoir chance of sufficiency times seal chance of sufficiency gives you a single prospectivity surface for the lower 48 states. The brighter regions on this map are where source, reservoir, and seal all coincide, which is exactly what you need for hydrogen to have accumulated and stuck around. This is genuinely one of the first data-driven, uncertainty-aware prospectivity maps for natural hydrogen at a continental scale. This work isn't finished. Prospectivity mapping of Alaska is currently in progress, a very different geologic setting from the lower 48. And this approach is starting to go global, with active discussions underway with researchers in Canada, Australia, Brazil, Colombia, Finland, and several other countries. If this model holds up, it's likely to become a template applied well beyond the United States. So what does this field actually need to mature? 5 things, roughly. Refining the hydrogen system model itself, developing better surface and subsurface exploration techniques specifically to identify hydrogen flux, modeling tools for testing hypotheses and evaluating different system concepts, engineering approaches for actually producing hydrogen efficiently from the subsurface, and tighter integration across geology, geochemistry, and geophysics. Here's the encouraging part, though, this isn't starting from zero. Much of the needed expertise already exists, just scattered across petroleum, geothermal, and mineral exploration. Natural hydrogen sits right at the intersection of all three. On the exploration side, there are 2 broad approaches. Remote sensing includes things like LiDAR and hyperspectral imaging. This rainbow image, for example, is a hyperspectral scan being used to spot surface indicators of hydrogen systems. The other approach is soils and soil gases, low-cost geochemical sampling, advanced techniques like noble gas and clumped isotope analysis, downhole gas characterization, and even environmental DNA sampling to detect microbial signatures. It's not simple, though. There are real complications, including temporal and spatial variability in surface readings, artificially generated hydrogen from human activity contaminating results, and the need to account for efficient microbial removal near the surface. Below the surface, the toolkit looks a lot like modern petroleum exploration. Numerical modeling for feasibility studies and optimizing survey design. New seismic imaging methods specifically tuned for low-impedance contrast settings, like crystalline rock, where hydrogen systems often live. Integrated geophysics, combining electromagnetics, gravity, magnetics, and seismic to build a fuller picture. And increasingly, artificial intelligence and machine learning to integrate data across multiple scales and sources, which is exactly what a 3D geophysical inversion like this one is doing. One more modeling technique worth highlighting, reactive transport modeling. This shows 2 scenarios of hydrogen moving through the subsurface, advective and diffusive flux of both water and hydrogen. In the top scenario, without a hydraulic head drive, transport is relatively sluggish. In the bottom scenario, adding a 10 megapascal hydraulic head drive, you can see hydrogen transport and accumulation increase markedly. This kind of modeling helps predict not just whether hydrogen can accumulate, but how fast and where. Let's bring it all together. Large quantities of natural hydrogen exist in the subsurface. That part is no longer in serious doubt. What remains genuinely unknown is whether economic accumulations exist in producible quantities. Prospectivity of geologic hydrogen has now been mapped across the lower 48 US, with Alaska mapping ongoing. But there's still real work ahead. We need to better understand the processes that lead to accumulation, identify exploration techniques and strategies that actually work, and develop efficient engineering approaches for production. This field is moving from "is this real?" to "how do we actually find and produce it?" And that shift happened remarkably fast. So, natural hydrogen, a gas that's been forming in Earth's crust for as long as Earth has had water and reactive rock, sitting almost entirely outside the search image of a century of petroleum and mineral exploration. We now know it's genuinely everywhere. We have direct proof it can accumulate in Mali, and we have the first uncertainty-aware maps of where it might be hiding across the US. Whether it becomes a real part of the energy mix depends on exploration, engineering, and a lot more research, but this is one of the most interesting open questions in energy geology right now. If you found this useful, let me know in the comments what you'd like covered next, and I'll see you in the next one.